In the previous video, we began to work kinetic theory, in which we applied Newton's laws and our concepts from earlier in the course, such as pressure and momentum and energy, and we have derived down to this point where we have the pressure on the wall, which is due to the gas pressure, times the volume of the gas is equal to 2/3 times the number of particles of the gas times 1/2 the mass of a molecule times the average of the square of the speed of the particle. And if we look at this, 1/2 mass times the average of speed squared, this is the average kinetic energy. So K, the average energy for a single molecule, is 1/2 mv squared bar. So that's the energy of one molecule. N times that is the total energy due to kinetic of all the molecules. Now, in our ideal gas case, the only type of energy that these molecules can have is kinetic. So what we've really got here is the internal energy. This quantity, 1/2 m times v squared bar, this is the internal energy per molecule contained in the gas. And N times that is the total internal energy obtained by the gas. So we want to write that down. So PV, which kind of doesn't look very special or anything related to energy, is in fact 2/3 times the number of particles of U, the internal energy per molecule of the gas. And if we combine these two terms, is 2/3 big U, which is the total internal energy. Of the gas. Now, what's interesting is we've said earlier that this little u was related in some way, back in the zeroth law of thermodynamics, to the temperature in the Kelvin scale. It also tells us why T has got to be in Kelvin in just a second. I'm going to combine this result with our ideal gas law, which we experimentally found, to find a relation between U and T. So I remind you that we have the following. PV is equal to NKT, but we just said that it's equal to 2/3 N times U. This implies, therefore, that U is equal to 3/2 kT. So when you measure temperature in the Kelvin scale, you are actually measuring the average energy, internal energy per molecule of the gas. And if you multiply that by the number of molecules, you've measured the total internal energy. So let's go back and close the loop here. Remember that volume and pressure graphs that we had, and the fact that whether it was P or V, these graphs, if this was in Celsius, kept coming back and striking here at minus 273 degrees. PV is related to the energy of the gas. You can't have a negative energy in kinetic. I mean, what speed would that correspond to? 1/2 mv squared. What number do you put in for V to get none of it? It'd have to be an imaginary speed. All right? So the T had to be adjusted if it's really going to connect to energy, such that when the energy U went to 0, then PV went to 0, then there's no energy, T had to go to 0. And that's why, that's a scientific reason that this has to be 0 Kelvin. And that's the temperature, because only in the Kelvin scale are we directly connecting temperature to energy, and not to something like the expansion of a piece of metal. So the fundamental connection to temperature, the question that we started a long time ago, is that it's a measure of the internal energy per molecule of a gas. But we must use the scientific Kelvin scale. No other scale has any physical meaning. So when we measure T and N, we're finding the internal energy of the gas. But we're not having to add up all the energies of each gas molecule. Maybe one of them has 10 to the minus 31 joules. We do not have to add up 10 to the 26 molecules. All we need is the thermometer and a scale. With a scale, I can measure the mass, and if I know the gram molecular weight, I can determine the number of particles from Avogadro's number. And with the thermometer, I have T. And with those two things and nothing else, I've determined the total energy stored in the gas. Now, it turns out this depends on the way the gases and other things can store, so it's more complicated for solids and other things, and we'll go on to explain that in more detail later. But this is a wonderful result. So when you think of temperature, realize that you're telling me how much energy is stored in the gas. They're always related, internal energy and temperature. All right. So let me show you one more sort of question you could get asked about this. Let's say you had a glass of water. And this glass of water happened to be at 30 degrees C, which of course means that it happens to be 303 Kelvin. And you happen to have a bathtub, much larger amount of water, so the small glass. And that bathtub happened to have a temperature, and it was 303 Kelvin. What we're saying is the energy per molecule is the same. The total energy, the total internal energy, is greater for the bathtub. So when you say something is hot, when you put your hand in water, you're not really measuring the total energy. You're measuring the average energy of a molecule, because that's how hard it's hitting the atoms inside your hand. But the total energy, even for something with much less energy per molecule like the ocean, with a very low temperature, is much greater because it has a much greater number of N's. So the total energy depends on both N and T. Your statement about hot or cold depends upon the energy per molecule. It does not take into account the number. All things at the same temperature of two things, if you have two objects that are the same and at the same temperature, they have the same energy per molecule. Speed distribution. So one of the things that was found out, all the molecules are moving around at different speeds. One thing we know is that their velocity is 0, because some of them are going to the right, some are going to the left. So the average velocity is 0. The average speed, if we just take the magnitude, it's not 0. And in fact, it's no any one number. Now, Maxwell and Boltzmann sat down and, through great work, worked out exactly what that is. And if you look at this, if you take a case of speed and you take number of particles, you'll find that you get a distribution that looks something like this. Not quite as sharp as I would like it. There is some most probable speed corresponding to the peak. There's also an average speed, and there's something about how wide this spread is, which is related to the RMS. Now, I give you a couple of formulas that are useful to know in certain types of tests. Kinetic theory enables you to calculate the RMS speed pretty quick. We know that 1/2 mass times v squared averaged is equal to 3/2 kT. So therefore, the average of the square is equal to 3 kT over m. Another word for average is mean. And we saw we had a square. This means root. It means take the square root of that. Why? I'm looking for a speed, and this quantity doesn't have speed. It has the quantity speed squared. This is often called the uncertainty in a speed, or maybe delta V. It's a measure of how much those guys vary from your average. And you see that it depends upon the square root of 3 kT. There should not be a 2 here. That is a mistake. Another speed that's important is the most probable speed. This is the point of the peak. It depends on the square root of 2 kT over m. And last but not least is the average speed of a gas molecule. And if you did the statistics, it can be shown as being the square root of 8 kT over m. Notice that all speeds go down by the square root of m. So if you have 4 times the math, you're going to have half the average speed, half the most probable speed, and half the RMS speed. They all go up as the square root of t. Now, it turns out a useful thing to know if you're working in the units of electron volts, which we'll cover later in the course, is that the product of K times T is approximately 1/40th of an electron volt. This can be useful in making these type of calculations. Anyway, I wanted those equations to be in there because you will occasionally see problems with them. They're not something that I will probably test in this course. All right, we'll see you on another video.